Hello, my name is Tom Holoien and I'm a graduate student in the astronomy department at The Ohio State University. I'm also a member of the All-Sky Automated Survey for Supernovae, or ASAS-SN, and today I'm going to be discussing our recent paper titled The ASAS-SN Bright Supernova Catalog 1, 2013 through 2014. This is the first in a yearly series of papers that will be written by the ASAS-SN team on bright supernovae and their host galaxies, and it collects information from our first year and a half of operations. ASAS-SN is a long-term project designed to monitor the entire visible sky on a rapid cadence to find nearby supernovae and other transients. We accomplish this using 14-centimeter telescopes, giving a 4.5 by 4.5 degree field of view and a limiting V-band magnitude of roughly 17. ASAS-SN began real-time operations in April of 2013 with our northern unit, Brutus, consisting of 2 telescopes located on Mount Haleakala in Hawaii. Brutus was upgraded to 4 cameras in late 2013, and in May of 2014 our 2-telescope southern unit, Cassius, began survey operations from Cerro Tololo, Chile. Cassius has since been upgraded to 4 telescopes, allowing ASAS-SN to survey roughly 20,000 square degrees per clear night, covering the entire visible sky with a cadence of roughly 2 to 3 days. This paper collects information including coordinates, redshift, magnitudes, type, and offset from host for all supernovae discovered by ASAS-SN in 2013 and 2014. For comparison, we also collect the same information for all bright supernovae, defined as those with peak magnitude of 17 or brighter, that were discovered by other groups after May 1st of 2014, when ASAS-SN became operational in the southern hemisphere. We also include information on host galaxies of all supernovae in our sample, including UV through IR magnitudes from GALEX, SDSS, 2MASS, and WISE. In addition to some of the information provided in the tables in the paper, we also performed some simple analyses on the data we gathered in order to examine some of the trends. To keep our comparison sample consistent, we only include ASAS-SN supernovae discovered after May 1st, 2014, when ASAS-SN became operational in the southern hemisphere. This figure shows a breakdown by type of the ASAS-SN discoveries, the supernovae discovered by other observers, and the entire sample. The ASAS-SN sample most closely resembles an ideal magnitude-limited sample, but in all cases we would expect to see a greater proportion of type 1a supernovae and a smaller proportion of core collapse supernovae. The difference between the ASAS-SN sample and the supernovae discovered by other observers can be seen clearly when looking at their host galaxies and their offsets from the host nucleus. This plot shows the host galaxy Ks band magnitude and offset from host nucleus for all supernovae in the combined sample. Here, red stars represent ASAS-SN discoveries, blue squares represent discoveries by other professional surveys, and black circles represent discoveries made by amateur supernova observers. The corresponding lines represent the median offsets and magnitudes. While all professional surveys discover supernovae in less luminous hosts than amateurs, ASAS-SN clearly is less biased than other professional surveys and amateurs with regards to sources located nearer to the host galaxy nucleus. This trend is also apparent when the offset is measured in kiloparsecs instead of arcseconds, as the median offset for ASAS-SN is less than half that of the other samples. ASAS-SN's impact can also be seen when examining the number of supernovae discovered per month in 2014. In this histogram, red represents ASAS-SN discoveries, green represents supernovae discovered by other groups but recovered in ASAS-SN data, and blue represents supernovae discovered by other groups that are not recovered in our data. From May 2014, when ASAS-SN became operational in both hemispheres, onward, ASAS-SN discovers and recovers more than half of all bright supernovae. In addition, the average monthly number of supernova discoveries increases from 13.3 in the first 4 months of 2014 to 21.1 in the last 8 months. This implies that ASAS-SN is finding supernovae that would not be discovered if it did not exist. Finally, here we show a cumulative histogram of supernovae discovered at different peak magnitudes in our full sample. The red line represents only ASAS-SN discoveries, the blue line represents ASAS-SN discoveries and supernovae recovered by ASAS-SN, and the black line represents all supernovae in the sample. The green dashed line shows the number of supernovae expected in a Euclidean universe normalized to the full sample. While this cannot be used to determine supernova rates because it does not address the absolute normalization of the fit, it implies that the sample is roughly complete to a peak magnitude of about 15.8 and is roughly 50% complete at 17th magnitude. The analyses presented in this paper highlight the major impact that ASAS-SN is having on the discovery of bright supernovae. ASAS-SN remains the only professional project to provide an unbiased, rapid cadence survey of the nearby universe. and it operates in a region of parameter space that is largely only monitored by amateur observers who target bright nearby galaxies for their searches. It is our hope that by collecting and publishing the information in this catalog, we will create a convenient data repository which can be used for interesting population studies that may have an impact on fields such as supernova physics, cosmology, and time-domain astronomy. For more information on this work, or to view the catalogs, please see our paper which is posted on the archive. Thanks for watching.